In this video, I'm going to talk about calculating stellar radii. Please take a moment and read the success criteria I plan to cover in this video. Now, let's take a moment and remind ourselves of Wien's displacement law. I also have another video called Blackbody, Wien's law, and Stephan-Boltzmann's law that you might want to watch. It has more detail than what I'm going to talk about right now. So just as a quick reminder, we have intensity here on the y-axis and wavelength on the x. And if we look at the spectrum given off of anything, then we find that it gives a whole spectrum of electromagnetic wavelengths. And at the point where the peak happens, we know that that maximum wavelength value times its temperature in Kelvin will equal 2.9 times 10 to the minus 3. That's the relationship between the wavelength and its temperature. So if I'm going to use Wien's law to find the temperature or relate it typically from giving a wavelength, I also need to be able to find its luminosity. Very often we're going to use this equation here, the Stephan-Boltzmann law, and we have the luminosity. Now if it's a black body like a star, this value of emissivity is 1. Stephan-Boltzmann's constant, one of my favorites, 5.67 times 10 to the minus 8. It's also in our data booklet. This is the surface area. Don't forget it's a sphere, so that would be 4 pi r squared. And the temperature again in Kelvin to the power 4. It does have to be in Kelvin for this equation to work. So I might have Wien's law to get the temperature. I might then have a Stephan-Boltzmann law to get the luminosity. Or here is a Hertzsprung Russell diagram, which is luminosity versus temperature. So if the question has that, I might have to read the graph. Don't forget, this is a logarithmic scale in both directions, and temperature looks backwards than normal. Again, I have a video on Hertzsprung Russell diagram that you can go check out if you want more detail. My dotted line here is just showing the value of 1, and this is the luminosity of the sun. So I could put together our equation for a sphere and Stephan-Boltzmann's law, and if I rearrange, I will get the radius of my star being the square root of the luminosity over 4 pi sigma temperature to the power 4. And so that's one of the ways that I could be asked to find the stellar radius. Two really important things I want to point out are information we have in our data booklet. We have that there's the one astronomical unit. That is the average distance from the sun to the earth. We are also given that this value is 1.50 times 10 to the power 11 meters. So if we need that distance, they are expecting us to be able to use this. The other thing we have is this thing called the solar constant. Now, if we take a look at my units, which are incorrect, the units are watts per meter squared. Why is that important? Well, that is going to be an intensity. And many people incorrectly think that the solar constant is actually the luminosity, but the luminosity is measured in watts, so that means it's a power. So let's think, if I have just this information, can I find the luminosity of the sun? Well, brightness is going to be luminosity over 4 pi d squared, d being the distance from the earth to the sun. Now, if I move that around, the luminosity of the sun at the earth, and we usually call this, or we usually signify this with the circle and dot in the center, that would be our brightness times 4 pi d squared. And remember, this is the brightness as measured at the earth, our solar constant, 4 pi d squared. This is the distance from the sun to the earth, so where we're going to be measuring this brightness. So if I put all of these in, and I pick up my handy dandy calculator, and I'm going to get, now let's think, it's luminosity, the units are watts. So given this information that I have in my data booklet, I can find the luminosity of the sun. For the other stars, I'd have to either be given the equivalents of the brightness and their distance, or I can get the information, like I said, from Wien's law and Stephan-Boltzmann's law, or from a Hertzsprung Russell diagram. So let's go check out some examples. Now that we've gone through the theory, and before we get to the questions, has this helped you? Consider helping me out by telling your friends about the videos. Consider subscribing or liking the video. Thanks for your help. Okay, I have no idea how to pronounce this star's name, and no, I didn't take the time to go Google it, but let's say this star has a peak wavelength of 1.93 times 10 to the minus 7 meters, and its luminosity is 3,150 times that of the sun. It'd be even better if I had a question here. What is its radius? Okay, so let's go through the details here. My luminosity will be the luminosity of the sun times 3,150. And I just found that on the screen before. And I'm just going to use my value I found. If this was a question on the exam, yes, you'd be expected to calculate it out. It'd probably be that in part A, and this would be part B. I'm going to have to times that by 3,150, picking up my handy-dandy calculator. Now, I'm not done. I need to have a temperature if I'm going to be able to find the radius using the Stephan-Boltzmann law. And I do know its peak wavelength, so I'm going to use the Wien's law there. So remember, lambda max times the temperature equals, I know I have some extra decimal places there. That would be in Kelvin. So remember, I put the radius into our Stephan-Boltzmann's law. I'll walk through it one more time for you. The area will be the surface area of the star. So that will be the radius of the star squared times the temperature to the power of 4. And if I rearrange that around, my radius will equal luminosity over 4 pi sigma temperature to the power of 4. I'm going to substitute my numbers in. And again, with my handy-dandy calculator, now I'm going to round it to the appropriate number of significant figures. And my star's radius is 5.8 times 10 to the power 9 meters. So we need to now estimate our radius of Capella. Here it is right here. I'm just going to circle it so it stands out. Now, it's chosen so I can easily read the numbers because I don't have a lot of guidelines on here. And it looks like my luminosity is going to be 100 times the luminosity of the sun. And if I read my temperature, again, without the guidelines, there's only so much we can do. I'm going to say it's 5,000 Kelvin. I'm going to substitute it into the same equation. I'm not going to rearrange it again. So it was R over root L 4 pi sigma temperature to the power 4. Putting in my numbers, and picking up my handy-dandy calculator, 9.3 times 10 to the power 9 meters. Now remember, definitely always read the labels on these graphs. In this case, because it says luminosity and in luminosities of the sun, I had to take my value and multiply by that. So please read the success criteria one more time. I hope I've given you examples and explanations so you can say yes to our success criteria.